Hey everybody, Mr. Grove here. Today we're going to talk a little bit about inclined planes. So let's go ahead and jump into the examples here. The first one, we have a 10 kilogram block. It's going to slide down the plane, and we want to know what acceleration it's going to slide down that inclined plane with. So first things first, we need to draw in our force diagram forces. So weight is always going to be straight down. So that'll be our force weight. And then our force normal, by definition, is always perpendicular to the forces in contact. And then if the block is sliding down, we know friction is going to be causing it to be a force up. So our friction is always opposite our motion. The problem is these forces are not all in the same plane. And so we will need to break this force weight into its x and y components. Okay, so we would have a force weight y and then a force weight x. And now our force weight x will be in the same linear plane as the friction, and our force weight y will be in the same linear plane as the normal. We have to choose a positive and negative direction. So what do we want to be positive? I like to keep my friction negative, so that means sliding down would be positive and negative here. And then in this direction we can just choose normal as positive, and then the force weight y direction is negative. And so when we set up our force equations, we would have force weight x is in our positive minus friction, and that's always going to be equal to ma or 0. So in this case, it's going to be ma because we are accelerating down the inclined plane. If it were constant speed, or if it were at rest, then it would be 0. For the other side, so we got our force normal minus force weight in the y, and that's going to be equal to 0 because we're not even moving in that direction there. Okay, so that gets our force equations. Now let's take a look at this little vector breakdown of the triangle. So we know 30 degrees was this angle here, so that means this is going to be 30. Our right angle is here, and this is going to be our right angle. So this triangle and our big inclined plane triangle are what's called similar triangles. And so being similar, their angles will be the same. So our 30 degrees is going to be right here. So to get force weight, we would just take mass times gravity. So that would be 10 kilograms times our 9.8 meters per second squared, and that's going to give us 98 newtons. Okay, for force weight y, we'll use our trig functions. So sine of 30 will be our opposite, so that's our force weight x, over adjacent, which was opposite of our hypotenuse, which was 98. So when we solve for force weight x, we get 49 newtons. And then for force weight y, so that's going to be cosine 30, it's just going to be adjacent over the hypotenuse. So cosine 30 equals force weight y over our hypotenuse of 98. So when we solve for force weight y, we're going to get 84.9. You do need to make sure that you are in degree mode, not radians. Okay, now we have some stuff that we can start to put into our equations. So we know force normal is going to equal force weight y, which over here we know was 84.9. Okay, so that's set up there. Now over on this equation, which would be these guys here, we know force weight x was 49 minus our 84.9 0.9. Force normal times our mu value was given to us in the problem of 0.3. And that's equal to our mass, 10 kilograms, times our acceleration. Okay, so we can solve for acceleration to give us 2.353. And that would be meters per second squared. And that would be sliding down the plane. Okay, so that's how you would do that example. This one, let's try and push it up the plane. So we want to know what force would be needed to push the mass up the inclined plane at a constant speed of 3 meters per second. So we have the same incline, we have the same mass, we have the same friction. So let's draw our forces in. So we're still going to have force weight straight down, force normal perpendicular. We're pushing up the plane, right? So we're going to have a force push. There was no push on the first example because we were just releasing it down. And since we're moving up the plane, that means friction will have to be opposite. So again, we'll have to break down our force weight into weight y and to weight in the x. And we're going to need a positive and negative direction. I like to keep friction negative, so we're going to go positive and negative, and then we can just go up as positive and down as negative. So when we put in to our last solve for our force weight, so that's going to be our mass times our gravity. So that's going to give us 98 newtons again. For our force weight x, so we know force weight x, using our trig functions from the last example, is going to give us force weight times sine of 30. And that's going to give us 49 newtons, sorry. And then our force weight y will be our 98 force weight times our cosine of 30, and that will be our 84.9. So 84.9 newtons. Okay, we got that taken care of. Now let's do our equations. So up, so we got our positive force push minus our force friction equal also minus our force weight x, and that's going to equal ma or 0. Well, we're at a constant speed here, so that would be 0. Okay, then the other one, let's see if we can squeeze that in. Our force normal minus our force weight y will equal 0 because we are not even moving in this up-down direction here. Okay, so those are our force equations. So let's put in what we know. So force normal is going to equal force weight y, and we know that from over here being 84.9 newtons. So over here we have our push minus our friction, so that's normal times mu, so 84.9 times our mu is 0.3, and minus our force weight x, which we solved for is 49, and that was equal to 0 because we were at a constant speed. So when we solve for our force push, we would get 74.5 newtons. Okay, so one being slid down, one being pushed up. Let's switch it over. Now on this one, we have kind of a setup where we have a mass, and it's being connected to a string over a pulley, which has another hanging mass on it. And so we're gonna, this is at rest, we're gonna let this go, and we wanna know what is the acceleration that this thing is gonna have. Okay, so we still have to do our forces, so we know force normal, perpendicular to the planes, force of weight, straight down. Our string is trying to pull us up. And then the last thing is friction. So here's where we have to make a choice. Do you think this is going to slide down, or do you think that 4 kilogram mass is going to pull this up? So it's really not a huge deal if you choose wrong. It's a pretty quick and easy fix. But let's go ahead and feel like this is probably going to slide down. So if that's the case, then that means our friction will be up as well. Okay, so let's go ahead and break our force weight into the y and the x. Which means then our formula is going to be force weight x minus force friction minus this force of pull. And that's going to equal ma, or 0. Well, we think it's starting at 0, so if it moves at all, it's going to be accelerating. So therefore, it's going to be equal to ma. The other side then, and that was choosing positive as down. The other side, if we choose our normal as positive, so that means we have force normal minus force weight y equals 0, because we're not even moving like that. And so you should be seeing a familiar pattern with inclined planes there. And so now we've got our forces. Let's go ahead and do our triangle work. So force weight would be mass times gravity. Well, we know 10 kilograms times 9.8 would give us 98 newtons. Force weight y is going to be equal to cosine. So cosine 60 times 98. So that ends up being 49 newtons. And then force weight x, slide that over a little. Force weight x is going to give us the sine of 60 times 9.8, no, I'm sorry, times 98. Let's fix that. So sine of 60 times 98, our force weight. And that will give us 84.9. So now we can plug in to where we know. So force normal equals force weight y, which we set up here was 49 newtons. And then over here we have our force weight x, which we know was 84.9, minus our friction. So friction is normal times mu, so 49 times our mu value was 0.3 minus the pull. Now the pull is coming from this mass here. So that mass, the force of weight, is what's causing the pull. The pulley just redirects it, so it doesn't change the amount of the force. So for this one, we would have 4 kilograms times our 9.8 to give us our weight, and that's our pull, so that would end up being 39.2 newtons there. So for the force pull, we'll put 39.2 newtons in, and that's equal to ma. Now we have two masses. The mass that we're always interested in is this one right here that's sliding on the plane. So 10 kilograms, and then that will be times our acceleration. Okay, so there we go. Solve for A, and you get 3.06 meters per second squared. It's a positive number, so that means it is accelerating in the positive direction, which we said was down, which means that we chose correctly. Okay, so when we arbitrarily chose positive, negative, we chose correctly. This would indeed slide down. The next problem, will show you how we can fix that if we accidentally chose incorrectly, and we would know that we were wrong because this would be negative. So let's take a look at this last one. A little bit different values. So we have a 10 kilogram mass, 8 kilogram mass. Our friction is slightly less, and our angle is 20. So let's put our forces in. So we got our normal force, we got our weight, we got pull, and we have to assign friction. So you might be thinking, well, 10 kilograms is heavier than 8, so I'm going to say it's going to slide down like the last problem. So let's see if that works. So that means friction would be up like this. We can put our force weight Y in and our force weight X in. So let's choose positives and negatives. So again, keeping our friction negative if we're saying it's moving down, so friction would be up, so positive, negative, and we'll go positive and negative here. So that means our formula would be force weight X minus friction minus the pull equals MA, because we are accelerating from rest. And then the other side would be force normal minus force weight Y equals 0, since we're not moving in that direction. So 10 kilograms to get our force weight would be 10 kilograms times 9.8. So that's going to give us 98 newtons again. This time our force weight Y is going to be sine 20, or I'm sorry, cosine 20. So cosine 20 times our 98. Okay, and that, that should give us a value of 92.1. Okay, and then our force weight X would be sine 20 times 98, and that's going to give us a value of 33.5. Okay, so let's put some numbers in. So force normal equals force weight Y, which equals, in this case, 92.1. Okay, over here we have our force weight X, so 33.5 minus friction, which would be normal, 92.1, times mu, 0.15. So mu's here. Minus our pull, so for that we'd take our mass times our gravity, so 8 times 9.8. And that's going to give us 78.4 newtons there. Okay, so minus 78.4 equals MA. So M is 10, because that's the one on the incline, and A. So solve for A, plug and chug, and we get negative 5.87. So that just tells us we chose wrong. Okay, that this is not going to slide down the plane. In fact, it's going to slide up the plane. So what we need to do then, it's a super easy fix. We basically just take this one equation and flip all the signs except keep your friction negative. So we'll flip this first sign, minus 33.5, keep the friction negative, minus 92.1 times 0.15, and then flip this next sign, so that's plus 78.4 equals 10 times A. Okay, so again, we're just flipping the signs. So flipping this sign, or keeping friction the same, and flipping this one. So negative, same, positive. Plug and chug again, and now we get acceleration to be a positive 3.1 meters per second squared, and that will be up the incline. So that just tells us that it is actually sliding up the incline as it goes up. So that 8 kilogram mass was enough to pull it up, which should kind of make sense. That's a really shallow angle, and our friction was only 0.15. So that is inclines, and I hope that was helpful. And as Kinley is telling me to say, don't forget to smash that like button.